Hey everyone, Mr. Schachter here to talk about implicit differentiation. In this video we're going to use implicit differentiation to calculate the derivative of multivariable functions, and we're also going to connect the process of implicit differentiation to the chain rule. Let's get started. So implicit differentiation is all about taking the derivative of things of multivariable. So we're no longer just considering x to be our variable. In this problem, we're going to assume y is a variable. We're going to ask what's the derivative of 3y to the second with respect to x? Well, in order to take the derivative of anything, you just have to use your normal appropriate rules. Taking the derivative of 3y squared would just be a nice power rule. So it would be the 2 comes down, multiplies with the 3 to get 6y to the first power. But then the chain rule says you need to multiply by the derivative of the inside. Well, the derivative of the inside, in this case, the inside is just y. The derivative of y with respect to x is dy dx. So that is just the derivative of 3y squared with respect to x. It's 6y dy dx. So this is different from if I were to just ask you what's the derivative of 3x to the second power with respect to x. The derivative of this is simply using your rules again. Y prime is equal to 6x to the first power dx dx, because I'm taking the derivative of x with respect to x. But that just goes away because dx dx is the same thing as 1, which is unnecessary. So whenever you're taking the derivative of a variable that matches the respect, you don't really need to chain it in regards to its respect. But when you take the derivative of y with respect to x, you do need to chain that inside. So here's the big picture. Take the derivative of anything with a y with respect to x, you add a dy dx. You chain that dy dx. Okay? Here's the process for implicit differentiation. Number 1, differentiate both sides of the equation with respect to x. Number 2, collect the terms of, with dy dx on one side. Number 3, factor out the dy dx's. And number 4, solve by isolating the dy dx's. Let's try an example. This one says to find the derivative of x squared plus y squared is equal to 4. Now keep in mind, this is not like f of x equals or y equals anymore. So I'm not really able to write notation like f prime of x equals, because there are multivariables here, right? I don't actually have a nice clean equation. So instead, what I'm going to do is just kind of write like the derivative is equal to. So we'll write deriv, and then we'll go and solve it. So if I take the derivative of x squared with respect to x, I follow my normal rules. That's just simply 2x, right? It would technically, I would need to chain a dx dx, but it's not necessary because it's 1. I would add the derivative of y to the second with respect to x. Well, use your normal differentiation rules because you're taking the derivative of a variable. That would be 2y to the first power. But then you would need to multiply by dy dx, because that's the chain rule coming into play. You're multiplying by the derivative of the inside. The derivative of the 4 is, of course, 0. Your goal in implicit differentiation, isolate the dy dx. So let's subtract 2x from both sides. So we'd get 2y dy dx is equal to negative 2x. And then divide both sides by negative or by positive 2y. And we get that dy dx is equal to negative x over y. So this is the derivative. The derivative of this function with respect to x is negative x over y. Let's try another example. To the right, you'll notice an ellipse. The ellipse formula provided in example 2 asks for the derivative of that ellipse. In order to solve this problem, you need to take the derivative of the entire problem with respect to x. So let's go ahead and try that. So let's do derivative is equal to, derivative of x squared is just 2x. No need to chain because it would be dx dx. The derivative of negative xy is actually going to be negative, but then parentheses, I need to product rule it, right? Because it's x times y. So the derivative of, we'll go product rule, says first function x times the derivative of the second. Well, the derivative of y with respect to x is just simply 1 dy dx. So I'm just going to write dy dx. Plus the second function times the derivative of the first, which is 1. Close parentheses, there's my product rule. Plus the derivative, of y squared with respect to x is 2y to the first dy dx. And that is equal to the derivative of 7, which is 0. So now what I'm going to do is try to group up my dy dx terms, get them on one side of the equation, and I've got my derivative. So let's distribute the negatives. So 2x minus x dy dx minus y plus 2y dy dx is equal to 0. Now it looks like we have two copies of dy dx. I need to keep those on one side of the equation, and I need to move everything else to the other side of the equation. So let's see if I could do this. So let's keep the dy dx's on the left. Let's move over the terms that don't have dy dx. So that's a positive 2x going to the other side, so that'll be a negative 2x. And I'm also going to move over a negative y, which would be a positive y. And then on the left side, let's factor our dy dx out. And what's left is negative x plus 2y. So that looks like everything. Now all I need to do is divide both sides by negative x plus 2y. So my derivative dy dx will now be isolated equal to negative 2x plus y divided by negative x plus 2y. And this is considered to be my first derivative. The goal now is to find the equation of the tangent and the normal at negative 1, 2. Well, our job is to just simply plug the values of the x and y coordinates into the derivative. Only this time it's a little more interesting because we'll actually use both x and y in our derivative formula. So the slope is equal to negative 1, 2 plugged in the original plugged into the derivative. So this is going to be negative 2 times the x value plus the y value, all divided by negative times the x value, plus 2 times the y value, which is the 2. So let's find the slope. Numerator is positive 2 plus positive 2 is positive 4. Denominator is positive 1 plus positive 4, which is positive 5. So that tells us that this is the slope of the tangent. The slope of the tangent is 4/5, okay? We could also really quickly find the slope of the normal. It's just the opposite reciprocal. So negative 5/4 is the slope of the normal. Now the one thing I'm missing is the coordinate point. I need to go and find that. But actually, I was provided it. So in this case, I've already got the point. I can just write my tangent. My tangent is y minus y1 is equal to slope parentheses x minus x1, which turns to plus. This is my tangent. And my normal is just the same thing with the negative 5/4. Y minus 2 equals, oops, I was about to write the tangent slope again, negative 5/4 parentheses x plus 1. And this is my normal. So not much changes when you're solving for the tangent and the normal of a problem involving more than one variable. Alright, example 3 says to find the derivative of x plus tan xy is equal to 0. We're going to start out by just taking the derivative of x, and the derivative of x is just 1, plus the derivative of the tangent function is secant squared of the angle xy times by the derivative of the angle xy, and we're going to have to use product rule there. So this is first function times derivative of second, which is dy dx, plus the second function, which is y, times the derivative of the first, which is just 1, is equal to 0. The derivative of 0 is still 0. So let's get our dy dx alone. So the first thing I can do is move over the 1. So it would be secant squared xy times x dy dx plus y is equal to 0. And then let's divide through, oops, not equal to 0, equal to negative 1. Going to move over that 1. Let's divide through by a secant squared xy. So we get x dy dx is equal to negative 1 over secant squared xy. And I know secant squared xy on the denominator is just going to go up to the numerator and become a cosine. Well, it looks like we also forgot our y here. Forgot that y. So this is going to be x dy dx plus y is equal to negative cosine squared xy. And then we can subtract y from both sides, and then we can divide by x. So we'll have dy dx is equal to negative cosine squared xy minus y, all divided by x. And this is our derivative of the function above. Alright, let's close with this example. It says find the points on the graph where the slope of the tangent is negative 1/3. So essentially to solve this problem I just need to set the derivative equal to negative 1/3 and solve. So let's find the derivative first. So the derivative of x is just 1 plus the derivative of xy is the product rule again. So it's x times dy dx plus y times the derivative of x, which is 1, plus 4y dy dx, got to chain that dy dx, is equal to the derivative of 6, which is 0. So if I just drop the parentheses, because this is addition, it's not really necessary, and I can get rid of the times by 1 because I don't really need that. I'm going to take the terms that have a dy dx in them, and I'm going to factor out the dy dx. So it would be dy dx times x plus 4y is equal to, I'm going to subtract the two terms that did not have a dy dx. So it would be negative 1 minus y. To get dy dx alone, I just divide by x plus 4y, divide by x plus 4y, and I get that dy dx is equal to negative 1 minus y over x plus 4y. And the goal now is to just basically set this equal to negative 1/3 and solve. So I get negative 1 minus y over x plus 4y is equal to negative 1/3. And if I want to cross multiply and solve, I just need the negative to belong to one part, so I'll just put the negative on the bottom. I kind of noticed that the top left piece has some negatives in it already, so if I multiply by a negative, I think it's going to actually work in our favor and kind of all turn positive. So let's see what happens. The negative 3 times negative 1 is positive 3, and then negative 3 times negative y is plus 3y is equal to x plus 4y. So let's isolate x and get it in terms of y. I have to minus 4y from both sides, giving me x equals 3 minus y. So now that I know that x is 3 minus y, I can go back to my original equation and plug in x minus 4y. So I'm going to write this down. Again, we'll use a different color, kind of transitioning the problem. It's x plus xy plus 2y squared equals to 6. And I'm going to plug this in for x. And we're going to solve. So let's see. We get 3 minus y plus 3 minus y all times y plus 2y squared equals 6. And then we're going to solve, use the little distributive property. So we get 3y minus y squared, 3 minus y plus over here plus 2y squared is equal to 6. So let's see if we can solve this thing. I have positive y squared. So those are good. And then 3y minus y is plus 2y, and those are all set. And if I minus 6 from both sides, I have minus 3 equals to 0, and I accounted for everything. So I could factor this. Shouldn't be too bad. Just going to be y plus 3, y minus 1 equals to 0. So I get that y is negative 3, and I get that y is positive 1. So suppose we let y be negative 3 first. So I'm going to go up to my equation. X is equal to 3 minus y. So if I say x is equal to 3 minus y, and solve, x equals 3 minus negative 3, x equals 6. This gives me the coordinate 6 comma negative 3 as one of the points. And if I try another one, I let y be 1, and I know x is 3 minus y, and x is 3 minus 1, so x is 2. So the xy coordinate pair is 2 comma 1. So these 2 points together are the solutions. That's when we have the points in which the graph is, slope of the tangent is equal to negative 1/3.